You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Backups serve as one of the most fundamental safeguards in cybersecurity, with goals that extend beyond simply copying files. The true purpose of a backup is to guarantee recoverability, integrity, and availability of both data and systems. Recoverability means the data can be restored to its original state when needed. Integrity ensures that restored data matches the original without corruption or tampering. Availability means backups are accessible within timeframes defined by business requirements. For example, a hospital backup system must ensure patient records are intact, accessible, and restorable quickly, because delays or errors could directly impact patient care. There are several types of backups, each offering unique trade-offs. Full backups capture all selected data, creating a complete copy but requiring more time and storage space. Incremental backups only copy data that has changed since the last backup, making them efficient but requiring the entire chain to restore. Differential backups capture all changes since the last full backup, creating a middle ground between speed and recovery effort. For instance, an organization might run a weekly full backup with daily incrementals to balance resource consumption with recovery needs. Selecting the right combination depends on business tolerance for downtime and data loss. Retention policies define how long backups are kept and must align with both business and regulatory requirements. Short retention may save on storage but risks losing valuable recovery points, while overly long retention can drive up costs and introduce compliance violations. For example, healthcare providers may need to retain patient data for years to satisfy HIPAA rules, while financial institutions often follow strict retention schedules tied to auditing requirements. Mapping retention windows to both operational and legal obligations ensures that backups are not just technical safeguards but also compliance tools. Backup scope determines what is protected and how complete recovery will be. System image backups capture entire machines, including operating systems, applications, and configurations, enabling full rebuilds. File-level backups provide granular recovery, but may not preserve system states. Application-consistent backups ensure that databases or enterprise applications are captured in usable form, avoiding corruption when restored. For example, restoring a virtual machine image may bring a server online quickly, while file-level backups help recover accidentally deleted documents. Defining scope ensures organizations can recover not only files but also operational capability. The choice of backup media significantly influences resilience. Disk-based backups offer fast recovery but may be vulnerable to ransomware. Tape remains a cost-effective option for long-term archival, though slower to restore. Cloud snapshots, particularly immutable ones, provide scalability and resilience, while air-gapped backups remain disconnected from networks to resist malware. For example, a financial firm may combine daily disk backups for fast restores with monthly air-gapped tape copies for ransomware protection. Media selection ensures backups align with both performance and security requirements. Separation of duties is an important principle in backup administration. The individuals responsible for creating and managing backups should not be the same as those authorized to perform restores. This prevents abuse, whether intentional or accidental, and creates accountability. For example, an attacker who compromises a backup administrator account should not automatically gain authority to delete or restore data. By enforcing separation of duties, organizations strengthen the trustworthiness of backup operations and align with broader governance frameworks. Encryption is essential to protect backup data, both at rest and in transit. At-rest encryption ensures that stolen media or compromised cloud storage does not reveal sensitive information. In-transit encryption protects data during transfers between primary systems and backup repositories. For example, encrypting backup streams to off-site facilities prevents interception from exposing sensitive customer or financial data. Robust encryption, combined with disciplined key management, ensures that backups remain a defensive measure rather than a source of vulnerability. Cataloging and indexing make backups usable by providing rapid discovery of files and recovery points. Without proper indexing, searching through terabytes of backup data during an emergency can waste valuable time. Backup catalogs maintain metadata about backup content, enabling administrators to locate files or systems quickly. For example, if a legal team requests recovery of emails from a specific month, indexed catalogs allow pinpoint restoration rather than restoring entire archives. Effective cataloging turns backups into responsive tools instead of cumbersome archives. Versioning strategies preserve historical data and enable rollbacks to earlier states. This is particularly valuable in scenarios where recent versions are corrupted by ransomware or user error. For example, a university may need to roll back research files to a clean state before malware encrypted them. Versioning provides flexibility, ensuring that backups are not only about the most recent copy, but also about recovering from long-hidden issues. Having multiple restore points adds depth to the backup strategy. Backup scheduling must align with recovery point objective, RPO targets, and workload patterns. High-value, frequently changing data may require near-continuous backup, while less critical data may be backed up daily or weekly. For instance, transaction logs in financial systems may be captured hourly to minimize loss, while archival data is backed up less frequently. Aligning schedules to RPO ensures organizations balance performance and bandwidth demands with recovery goals. Data prioritization ensures that critical datasets receive more frequent or robust protection. Not all data is equally important. Customer records, financial transactions, and intellectual property deserve higher backup frequency and redundancy. For example, an engineering team's source code repository may be backed up multiple times a day, while marketing assets are captured weekly. Prioritization aligns technical operations with business value, ensuring resources are applied where loss would cause the greatest damage. Ultimately, backups remain one of the most fundamental yet frequently misconfigured controls. Too often, organizations discover too late that backups are incomplete, corrupted, or unrecoverable. Testing and governance transform backups from theoretical safety nets into reliable recovery mechanisms. A backup that cannot be restored is no backup at all. Reinforcing backups as both technical and organizational priorities ensures they fulfill their purpose, delivering dependable recovery during incidents, whether caused by ransomware, hardware failure, or human error. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Air gapping and immutability have become essential defenses against ransomware, which increasingly targets backups directly. Air-gapped backups are kept physically or logically disconnected from the primary network, making them unreachable to malware spreading through systems. Immutability ensures that once a backup is written, it cannot be modified or deleted for a defined retention period. For example, a cloud provider may offer immutable snapshots that cannot be altered even by administrators. Combining these approaches prevents attackers from corrupting recovery data, ensuring backups remain a viable last line of defense. Automated verification of backup integrity ensures that data is both complete and usable. Verification tools check that backup jobs finish successfully, validate checksums, and detect corruption or failed copies. For example, an organization may configure its backup system to automatically run validation scripts after each job, ensuring that encrypted files match expected signatures. Automated verification provides confidence that backups are not merely stored, but also recoverable. Without such checks, organizations risk discovering corrupted or incomplete backups only after an incident occurs. Periodic restore drills provide the most reliable proof of backup effectiveness. These drills involve actually restoring systems, files, or applications to confirm they meet recovery time objectives (RTOs) and recovery point objectives (RPOs). For example, a company may simulate restoring payroll systems to validate that data can be recovered within 4 hours and without significant loss. Drills also reveal practical challenges, such as missing dependencies or undocumented procedures. Regularly testing restores transforms backup strategies from theoretical safeguards into proven, reliable capabilities. Encryption key management is critical to maintaining the confidentiality of backup data. Backups should always be encrypted, but if keys are poorly managed, they can become a liability. Secure key generation, rotation, and revocation practices must be enforced, and access to keys should be tightly restricted. For example, storing backup encryption keys in a hardware security module (HSM) ensures that only authorized personnel can unlock backup data. Key management prevents backups from becoming a source of exposure and ensures compliance with data protection regulations. Off-site replication and geographic diversity provide resilience against regional disasters. Storing all backups in one location creates a single point of failure if natural disasters, fires, or regional outages occur. Replicating backups to geographically distant sites, such as a second data center or a cloud provider in another region, ensures survivability. For example, a business in a hurricane-prone region may replicate critical datasets to a site hundreds of miles away. Geographic diversity balances cost and resilience, ensuring continuity even in large-scale disruptions. Storage tiering provides a cost-effective way to balance backup speed and expense. Hot storage tiers offer fast recovery but at higher cost, while cold or archival tiers provide cheaper long-term retention with slower access. For example, daily operational backups may reside on fast disk-based systems for immediate restores, while monthly archives are stored on tape or deep cloud storage. Tiering ensures organizations can meet both RTO goals and budget constraints, assigning storage resources according to data's recovery value and frequency of use. Metadata and indexing practices significantly speed recovery operations. Metadata catalogs describe backup contents, while indexing allows administrators to search quickly for specific files, time ranges, or system states. For example, if legal counsel requests emails from a particular month, indexed backups allow pinpoint recovery instead of restoring full volumes. These practices reduce downtime and ensure backups provide efficient, targeted responses to recovery needs. Without indexing, administrators may spend valuable hours searching through massive archives during high-pressure incidents. Handling sensitive data in backups requires additional attention. Not all data needs to be backed up, and in some cases sensitive information should be masked, redacted, or excluded. For instance, temporary files containing raw customer data may not need preservation, while retaining them could create compliance risks. Where sensitive data is backed up, it must remain encrypted and subject to strict access controls. Carefully managing sensitive content in backups ensures compliance with privacy frameworks and minimizes unnecessary exposure. Retention cleanup automation prevents unbounded storage growth and compliance drift. Over time, backups accumulate, and without cleanup, organizations risk exceeding storage budgets or retaining data longer than legally allowed. Automated retention policies delete or archive backups according to defined schedules. For example, daily backups may be retained for a month, monthly backups for a year, and yearly backups for 7 years. Cleanup ensures backup environments remain efficient, legally compliant, and aligned with business objectives. Operational runbooks for restores ensure staff can act quickly during incidents. Runbooks provide detailed procedures for restoring files, folders, system images, or applications under pressure. For example, a runbook may outline exactly how to restore a corrupted database while preserving recent transaction logs. Having predefined processes reduces errors, speeds recovery, and ensures consistency. In a crisis, clear runbooks transform backups from static repositories into actionable recovery tools. Vendor-managed backup services introduce additional considerations around SLAs, recovery guarantees, and shared responsibilities. Providers may promise certain retention times, replication features, or recovery speeds, but customers must validate these claims and understand the scope of guarantees. For example, a cloud backup provider may guarantee data durability, but not recovery times. Organizations must clarify testing responsibilities, ensuring providers prove service reliability through audits or customer-driven restore drills. Vendor SLAs define expectations but must be backed by testing to ensure credibility. Ultimately, backup strategies succeed only when validated through regular restores and supported by governance. Without testing, encryption management, retention enforcement, and vendor accountability, backups can degrade into ineffective checkboxes. Governance ensures policies align with business and regulatory obligations, while testing provides practical assurance. Backups are not just about data storage, they are about guaranteeing recovery. A mature backup strategy closes the loop by proving that data can be restored, systems can be rebuilt, and operations can continue reliably after disruption. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.